So now we want to talk about the graph of a function and some about the behavior of those graphs. And so you should have experience with graphing functions in terms of x and y. You know, if you look at any equation that has x's and y's in it, so I don't know, say 3x plus 2y equals 7. That's a two-variable x and y equation that you have certainly graphed before. Graphing an equation like that is really not different from graphing a function because all we're doing is replacing the y with f of x. Now, not every two-variable equation is a function. Only some of them are. However, we can graph functions very similarly to the way we graph a two-variable equation. Again, because the y is really now just f of x. So the graph of a given function is the collection of ordered pairs x, f of x, such that x is in the domain of the function and f of x is the range. And once you collect all those ordered pairs, you put them together and you build the graph of a function. So if we were, say, looking at something as simple as, say, let's get rid of this, something as simple as, say, f of x equals 3x, okay? And we were to graph this function. We would have to find all the ordered pairs x, f of x, and we could use a x, f of x chart or table to do this that satisfy this function. Now, unfortunately, there are infinitely many x values that satisfy this function, so we can't find all of them, but if we found a collection of them, so I don't know, let's say a couple negatives, 0, a couple positives, and find the f of x that correspond to those. So if I plug -2 into this function here, I multiply it by 3, and that would give me my f of x, in this case -6, in this case -3, in this case 0, then 3, then 6. These would be just a collection of a couple of x, f of x ordered pairs that we could use to graph this function. So if we were then to set up an xy chart or an x, f of x axes, we could then plot these points, these ordered pairs, so -2, 6, 1, 2 is the -2 on the x, and -6, 1, 2, 3, 4, 5, 6. Down, this would be 1 point, -1, -3, that would be right here, then 0, 0, and then 1, 3 would be here, and then 2, 6 would be here, and if we collect all those points together along with every other point, we could then draw the graph of this function. Not the best graph, but this should be a line, and that is really no different than if I wanted to graph the equation y equals 3x, which again you have certainly done before. So, you know, that is fairly simple. Now, these functions graphs can range from very simple to fairly complex, and we would have to build to that point. Before we start graphing functions from scratch, one thing we should be able to do is to look at the graph of something and determine whether or not that is in fact the graph of a function. Now, functions have to follow the definition that each value of the domain has to get mapped to exactly one value of the range. And we can verify that by looking at a graph. Okay? We can verify whether that definition is upheld. And it's through something called the vertical line test. So if we place a vertical line anywhere on the graph, so if every vertical line meets the graph of a particular relation at most one point, then that relation would be a function, meaning that it follows that definition that we just talked about. So the idea here is if I look at any one of these and I put a vertical line anywhere on this graph, I can only hit at most 1 point, because that would then verify that 1x is mapped to 1y. So each x gets a y. Each x gets a y. Now all these x's happen to get the same y, but we've already said that that's okay. So this horizontal line, which is the graph of f of x equals, say, some constant c, would be, in fact, the graph of a function. Here's another one, f of x equals x. So if I plug in an x, the f of x is that same value. So 0, 0, 2, 2, 3, 3, 4, 4, 5, 5. These will all be points on this graph. But notice when I put a vertical line anywhere on the graph of this particular function, I would only hit at most 1 point, therefore verifying that this is in fact the graph of a function. So these two examples bring up the idea of lines and whether or not every single line is representative of a function. And so I pose that question. No matter what line I draw, will it always pass this vertical line test? And therefore, would every line or linear equation in fact be a function? The answer to that is no. Okay? Think about vertical lines. There are some equations of lines that result in a vertical line. Well, a vertical line would not pass the vertical line test. So, as long as it's not a vertical line, then yes, if it has some positive or negative slope to it, here or say this way, it would pass that vertical line test. If it's horizontal, it would pass the vertical line test. But if it were vertical, if the line I was graphing would be vertical, then that would not pass the vertical line test, because I put a vertical line right on top of that, I would hit definitely more than 1 point. All right, let's look at some other ones. Here's the squaring function, which we've already discussed. You put a vertical line anywhere on that. Because this is tilted outward in each direction, you would always go through 1 point. Again, what am I doing here? I'm saying that each x, this x gets matched to this y, this x gets matched to this y, this x gets matched to this y. Each x only gets matched to one y value. Now, whether it's a negative x, okay, which happens to get matched to the same y as the positive x, but that's okay. This x only gets matched to one of its y's, therefore it is a function, so this would pass the vertical line test. X squared is a function. But let's talk about circles for a second. If I put a vertical line right here, okay, I would hit 2 points. This x value, okay, matches up to this point and this point down here, and therefore it gets matched to this y value and this y value. So 1x, 2 y's. Well, 1x can't go to 2 different y values. That can't happen. So this circle doesn't pass the vertical line test. This circle does not follow the definition of a function. So a vertical line test right away tells me that any graph of an equation that represents a circle cannot be a function. This is the equation of this particular circle, x squared plus y squared equals 1. So you can look at the graph of any equation and determine whether or not that equation represents a function simply by using this vertical line test. Okay, so now we want to talk a little bit about behavior of the graph of a function. In that we want to talk about the idea of something increasing, decreasing, or being constant. So let's look at these 3 different definitions. First, a function f is increasing on an interval if for any x1 and x2 in that interval such that x1 is less than x2, then f of x1 should be less than f of x2. Now, that may be something you need to read a couple of times before it really sinks in, but it's actually a very simple idea. If your function's graph is going up from left to right, then it is following this definition. Because think about it, here's an x-axis. Here's one x value, let's call that x1. Here's another x value, let's call that x2. In this case, since x1 is to the left, x1 is less than x2. Now let's look at the corresponding points that these x values relate to on this function. Well, these points would then have corresponding f values. So this would be f of x1, and this would be f of x2. Based off the fact that x2's f value is higher, the x2 is bigger. The f of x2 is bigger. And so since x1 is less than x2, and then f of x1 is less than f of x2, my graph is going up from left to right, and we say that it is increasing. So this definition just basically means that I'm going up from left to right. So let's look at decreasing now. A function is decreasing on an interval if for any x1 and x2 in the interval such that x1 is less than x2 still. However, f of x1 is now greater than f of x2. Then if that happens, we say decreasing. Well, again, very simple, okay? If your graph is going down from left to right, and you look at still x1 and x2, still x1 less than x2, but look at the corresponding y values now, f of x1 is bigger than f of x2, even though the x1 and x2s are set up the same way as they were here. Now that happens because I'm going down from left to right. So if I'm going down from left to right, I am decreasing. And finally, a function is constant on an interval if f of x1 equals f of x2. Well, if two y values are equal, what that means is that I went horizontal. If I went horizontal and I look at these two x values, whichever one is bigger doesn't really matter, okay? In this case, it's set it up the same. The y value for each of these is exactly the same. They're equal, and that's constant. So if I go horizontal from left to right, I'm considered to be constant. So increasing up from left to right, decreasing down from left to right, constant, horizontal. I think that's a very easy concept for people to understand. I think the hard part is how we write our answers when a question says find the intervals for which the following functions are increasing or decreasing, and let's add in there or constant. Okay? So here are three different graphs. We'll look at each one independently, increasing, decreasing, or constant. So let's look at the first one, x cubed. And if you notice, this graph is going up from left to right the entire time. It's steeper in some spots than in other places, and it looks like maybe it goes horizontal right here in the middle. Okay? Now, for a split second, it does. Now, this is going to be hard for us to do without zooming in here to this center point. Also, it's a little hard for us to talk about what happens right here in the middle without talking about calculus a little bit. But purely, this thing looks like it is going up from left to right this entire time here. Maybe right here it looks like it goes horizontal for a second, and then it continues to go up from left to right. So we could say that this thing is increasing the entire time. If we omit kind of this, this questionable spot in the middle. So if I said this is increasing, this would be kind of controversial here in the calculus world, but we're going to say it anyway. It's increasing from negative infinity to positive infinity. Now, what does this interval represent? This interval represents the x values for which this is happening. That probably isn't the best way of writing this in terms of that's not 100% true. What really is happening is it's actually increasing from negative infinity to 0, and then it stops increasing for a specific second at the x value of 0 right here at the origin, and then it's increasing again from 0 to infinity. It's not something I can really get into right now because, again, kind of more calculus based as to what happens at 0 right there. But from a simpler standpoint, we could just say for right now it's going up the whole time. All right. Probably a bad example to start with. Here's a much better example. Okay, so let's look at this one. So in this case, this example is going up from left to right here clearly. Okay. and it's going up from left to right here. That's also very clear. It is going down from left to right here. Okay? Now, I need to state, when is this thing increasing? Well, let's use a different color. Okay? When is this increasing and when is this decreasing? Okay, I'll use ENC and DEC to represent increasing and decreasing. And so I want to represent it by the X values for which this is happening. So these X values in here, okay, let's use the same color. This is where it's going up. This is where it is going up. Okay, these are the X values for which that is happening, and this will go on forever, that direction on the X axis. And notice it stops here at -1. That's where it will reach its peak. Okay, and then it'll start turning back down again. And then from this X value all the way to this X value, where here is where it reaches its minimum, that's the interval where it would be then decreasing in terms of the X's. And then from that point on, okay, this is where it starts going back up again. So we represent the increasing and decreasing intervals by the X values for which this is happening. So I would say it's increasing from -infinity to -1. And it's also increasing from 1 to +infinity. It's decreasing between -1 and 1. Now notice I put parentheses here, 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 and here. Now why is that? Again, a little bit of calculus would be helpful to explain this, but basically this is where it turns around, okay? This is where it turns around from going down to up. And if it turns around from going down to up right here, it actually ceases to decrease and switches to increasing. And because the switch is happening right there at that point, it's neither increasing nor decreasing. A lot of this has to do with the idea of slope. And calculus is essentially the study of the slope of a function. And we could further explain this by using that idea, but for right now, simply saying the graph is going up from left to right or down from left to right, and these are the places where it switches from one to the other. It cannot be in the interval of increase or in the interval of decrease, hence we use the parentheses. Okay? All right, let's do one more. My graph clearly is going up from left to right here. It is horizontal here, and it is going down from left to right here. Now, if I think about the X values for which this is happening, all of these X values here, from -infinity all the way up to this X value right here, which is an X value of 0, I would be increasing. So I would say it is increasing from -infinity to 0. At 0, it stops increasing and switches, so I'm not going to include it in the increasing interval. Then, here's where it's horizontal. Right here, these X values right here is where it's horizontal. So I could say that it is constant from 0 to 2. Those are the X values. This X value is at 0, this X value is at 2. That represents this part of the graph in terms of the X's, so it is constant there. And finally, decreasing for these X values in here, and that would be from decreasing from 2 all the way to infinity, because this will go on forever this way, and therefore I'll use all those X's. So increasing, decreasing, and constant based off of the X values for which this is happening. And so I think when you look at the graph, people can easily see going up, going down, going up. But how do you write it? You write it in interval notation based off of the X values for which this is happening. The X values. Because there is only going to be one X for each point, and that X is unique to that point. The Y values are not. Okay, so let's talk about some very common functions and their graphs. We will look at each of these functions in a little bit more detail at certain points of the semester. However, we can easily talk about them right now. Let's start with the linear function. The linear function, f of x equals mx plus b, where m and b are constants. M would represent the slope, b would represent the y-intercept. These would be the graph of a line. Depending on what the slope is, that line would change in direction. But you should be very familiar with this because you are definitely familiar with y equals mx plus b, and that's all this equation is. So that would be your linear function. Linear because the graph is a line. We've already talked about some of these. The squaring function, okay? The squaring function, f of x equals x squared. The graph is a parabola. Here, where the vertex of the parabola, the low point is at the origin, 0, 0. We will talk about the parabola, the squaring function in far more detail later in the semester, but we should be familiar with that to a certain extent. We have the cubing function. The graphic is this graph right here. Sometimes people call it an S-curve. I don't know, it's not really an S, but nonetheless, it has this shape to it. That's your cubic function. You have your square root function here. And the square root symbol should go all the way across the x there. But the square root function has this kind of hook pattern to it this way. It starts at the origin. The domain for this is only 0 and positive, so it's only on this part of the x-axis. Notice there's no negative side here. There's no graph over on this side because you can't use these negative values. And so this little hook here would be the graph of the square root function. The absolute value function, which is the absolute value of x, a linear absolute value, I should say, more specifically. These two bars on either side are the absolute value symbol. Basically what it is essentially two lines in one, because the definition of an absolute value is based off of a piecewise function ultimately. X and negative x, depending on what x is. X is greater than or equal to 0, or x is less than 0. So it's really two lines, y equals x and y equals negative x. We're not going to talk about that in too much detail right now, but ultimately it's got this V pattern to it, where you have this V shape to it, where the point of the V is at the origin. That would be your absolute value function. And then there is finally the reciprocal function, 1 over x. F of x equals 1 over x is that function. And this is what we call a hyperbola, where we have these two catty-corner curves, this curve right here and this curve right here, representing our function. Notice it's the only one that's defined in multiple pieces. The reason being is the domain value 0, x, can't be 0. Okay, you can't have 0 in your domain. Therefore, this x value, which would be 0 right here, is breaking the graph into two pieces. We will discuss the reciprocal function when we talk more about something called a rational function, and that's one that has quite a bit of detail involved in it. Here's a fun picture that is often circulated online of this little stick figure who's using their arms to represent the different types of common functions. So absolute value, notices their arms are in the shape of a V. X is just a line, that's the linear function. X squared, we have the parabola. This is for a circle. It's not actually a function, but it's common. The square root, see the hook on their arm. The reciprocal, it's kind of getting a little weird here. Not quite, that's probably not the best one. And then just wiggly arms, could be whatever. Just a silly picture that is often circulated when it's talking about graphs of functions. One of the most common applications for functions is to talk about rate of change. We could talk about average rate of change. We could also talk about instantaneous rate of change. However, the instantaneous rate of change question really requires calculus. So with the knowledge that we have right now, we would only be able to talk about average rate of change. which you are already familiar with in that average rate of change is slope. And so if you were to take a calculus course, you would then see how we can use functions and rate of change to talk about instantaneous rate of change. Very common example for talking about this would be something about, say, velocity. In algebra, which we are currently basically in right now, basically anything before calculus in this realm is algebra. That's oversimplification, but generally we're in algebra. We talk about average rate of change. If you talk about in terms of velocity, we're talking about average velocity. And you could say, if I traveled 300 miles and it took me, 5 hours to do so, I could figure out what my average speed was. And that is basically looking at average velocity, or the average rate of change. That, in contrast to instantaneous rate of change, would not to say, well, I traveled 300 miles over 5 hours, what was my average speed? It is at the exact point when I was 2 hours and 32 minutes into my ride, how fast was I going at that specific moment? That would be instantaneous speed, which then relates to instantaneous velocity and therefore instantaneous rate of change. We cannot do that part of this without calculus. However, we can talk about average rate of change, so that's what we're going to do. And so average rate of change is really just slope, the change in y over the change in x. So when you see this little triangle, that's a delta, and so that's the change. So the change in y over the change in x, which are basically, if you're looking at 2 points, x1, y1 is 1 point, x2, y2 is another point on some particular function. We can measure the average rate of change for that function by doing the difference of the y's, which is the change in the y's, over the difference of the x's, the change in the x's. And you know this because this is the exact definition you have for slope. And what we're basically doing is not just doing this for a line, but we could find the average slope or the average rate of change for any function. This function is not a linear function. However, we can still talk about the average slope over this function, or the average rate of change. And so for this example, it'll be very simple. Our function is x squared plus 3. Our interval is 1 to 3. These are the two different x values. Say that's x1, that's x2. That's the interval of x we're working with. And so what I can do is I could say, what is f of 1 and what is f of 3? In this case, f of 1 would be 1 squared plus 3. F of 3 would be 3 squared plus 3. So this would give me 4. This would give me 12. So basically, I have 2 points here. I have point 1, comma 4. That's 1 f of 1. And I have point 3, 12. So using these 2 points, x1, y1, x2, y2, my average rate of change, can be calculated by doing 12 minus 4 over 3 minus 1, giving me 8 over 2, or 4. So the average rate of change over that period of the function would be 4. Now you're probably asking yourself, how is this an application of functions? Well, we could really relate this to a lot of different things. Like I said, it could be related to velocity or even speed. But first, let's just look at this function that we just talked about for one more second. So what we did is we looked at the average slope or the average rate of change from this point to this point. So what happens is this graph, this function is a curve. And when it comes to a curve, the slope is changing at every single point along this curve. It's not the same. In a line, the slope is the same the entire time. The rise over run, the steepness, is the same the entire time. Here, it's not. It's less steep here and more steep here. So, since the slope is different at each one of these values along this graph here, to talk about the average slope or the average rate of change, we can just think about an average. You average things by adding all your values up and dividing by the total number. So if I looked at all the slopes in here and I added all the slopes up and divided by the total number, I would then get the average slope from this point to that point. But a simple way of talking about this is essentially doing this. Let's just connect these 2 points. If I connect these 2 points with a straight line, the slope of that line that we just found is essentially 4. And that line gives me the average slope of the curve between those 2 points. Now, that is basically the introduction to the whole concept of calculus. We don't need to get into it too far, but just sort of relating what we just calculated to a curve and slope, which you already have some experience with, I wanted to give you a little bit of detail there. Here would be a more, relevant, more business-oriented, I don't know how to, quantify this question, but let's just say a more relevant application of rate of change. So rate of change is the change in one value relative to the change in another value. The change in y over the change in x, and change in output over the change in input. If we're taking, I keep going back to velocity, the change in distance over time. In this case, we're looking at money over time, and in this case, someone's salary. So let's look at it. In January 1983, Anna starts her new job and makes an annual salary of $38,000. By January 1986, her annual salary has increased to $46,500. And by January 1996, it has increased all the way to $232,500. What is the average rate of change of her salary between January 1986 and January 1996? So we need to think of how we're going to do this. Well, if we measure the change in salary as the change in salary over time, okay, because we're looking at a range of time, that could be the change in salary over the change in time. And we can measure that by how much the salary changed. Well, it went from $232,500 up from $46,500, and that took a span of 10 years. So the change was 10 years. I could say, if you really wanted to, I could say, 1996 to 1986, but that's 10 years. So if you do that calculation, right, looking at the change in those values, we could easily find the average change in her salary. So 232,500 minus 46,500. Okay, it's $186,000 divided by the 10 years it took to do that. She had an average rate of $18,600. That was her average change. Now, what is that saying? That's over the span of 10 years, on average, her salary was increasing by $18,600 in those 10 years. Okay? We could also then look at what happened in the first 3 years. Well, the first 3 years certainly was a far smaller average, but let's look at the first 3 years. So let's look at the change from 1980 from 1983 to 1986, right? What was that change? Well, from a salary standpoint, she went 46,000 up from 38,000, and it took 3 years to do that. Well, what was the average rate of change over those 3 years? Smaller span of time, but still we're just looking at averages. So the average in that span of time would be 46,500 minus 38,000 divided by the 3 years. Her average there was only 28.33. Okay? So as time went on, she was getting far bigger increases in her salary to the point where her average increased significantly from 1986 to 1996 instead of 1983 to 1986. This is something that typically happens when it comes to salaries. Salaries tend to increase on a scale that looks like that, where at first you don't have a very large increase, then as you get further and further in your career, your increases in salary tend to go up more. Inflation can also do this when salary increases due to inflation. The 80s were a very high inflationary period, and salaries, in this case, for Anna at least, increased correspondingly. Sometimes they do not. We just went through a big inflationary period recently. Unfortunately, salaries in some sectors did not necessarily increase at the same rate. That's a whole nother subject. But this is where you can see how average rate of change can be used. On average, her salary was increasing in the span from 1986 to 1996 at a rate of $18,600, whereas in the first 3 years of her career, it only increased at a far lower rate. Okay, so we can use